Well, thank you very much for the invitation. It's a pleasure to be here today. Okay, so today I'm going to talk about a family of foliations I'm going to introduce, but somehow the take is going to be slightly different from other talks that we have seen this week. I have the impression that here, like the crowd, people are interested in foliations in their own right because they're interesting objects. And I'd say that I come more from the study of geometric structures on surfaces, and in the course of studying those, we encounter interesting foliations, and they have to do with the geometry of the surfaces, and that's why I care about those foliations. And they're not examples of foliation displaying this behavior on this behavior, but because they're interesting because they tell me things about the objects I'm interested in. Okay. So the manifold, the complex variety in which everything is going to happen, is the moduli space of genus G surfaces with n marked points. And I'm going to introduce a family of foliations. Going to be f theta, where theta will lie in a parameter space. And somehow these foliations are going to tell me a lot of things about the geometry of certain flat structures. On surfaces. So my goal today is to take some time to explain to you how those foliations came about, the context and what you can do with them, and what are the interesting and natural questions you might want to ask. And yes. Okay, so I'm to start with introducing moduli spaces. So for some notation, so sigma Gn is the topological surface of genus G, with n marked points. It's moving a lot. And maybe I'll use sigma Gn star to be the this surface, the surface of genus G, minus n points. Which is, I want to think of in two different ways. This is really a surface with n marked points on them, and this is the surface punctured. Okay. Okay. So now I want to introduce the Teich space, which is the set of complex structures on sigma Gn, mod the action of diffeomorphisms which are isotopic to the identity. So what I mean by diffeomorphism of sigma Gn are those diffeomorphisms which fix pointwise the mark points. Okay? And the moduli space, which is the same space but mod out by orientation preserving diffeomorphisms instead of isotopic to identity. Okay, and so there is a natural projection, the Teich space to the moduli space. Okay. An important fact is that the Teich space is can be endowed with a structure of 3G minus 3 plus n complex manifold. MGN is a 3G minus 3 plus n complex orbifold. Okay, and this map is an orbifold covering that. So for many reasons, these are objects of interest for many different people, whether you're a geometer or an algebraic geometer, or even a dynamical system person. And yes. And somehow I want to explain how they relate to some structures on surfaces, which are flat structures with conical singularities. So maybe I should first draw a picture. So if you take R2 and you consider an angular sector in R2, got two lines, L1 and L2. You can take this angular sector and isometrically glue these two lines together to get a cone. And this defines, let's say, c theta, the cone of angle theta. Okay, and this is a surface with a flat metric away from the cone point, which is, from the point of view of Riemannian geometry, singular. Okay. Maybe I give some definition. So let's say flat metric, even though it's not a flat metric for the rest of the talk. A flat metric is a metric on sigma gn star. So I really want to exclude the singular point, which is flat and extends to the singular point, to the marked point, so how shall I put this, to cone type singularities. Okay, so what I mean by that is that if you look in the neighborhood of those marked points, your metric looks like a neighborhood of the cone minus the center of the cone. Okay. So a basic example of such a metric, if you take a cube in R3, nothing. You have a flat metric on each of the faces of the cube that you can extend to the complement of all the vertices of the cube, because you have two half planes that are bent along a line, so you can really rectify this type of singularities. But there's nothing you can do around the vertices, because when you go around, well, you see an angle. This is pi over 2, right? I take the regular cube, and I see 3 times pi over 2, and this is not 2 pi. So if it were Euclidean around this point, well, you'd see an angle 2 pi. So this defines a flat metric on sigma 0, 8, because the genus of this surface is 0, and you have 8 singular points, each of angle 3 pi over 2, which fails to be 2 pi. That's why it's not singular. Okay. Okay.
I think it's better to use this system. It might eventually break.
Thank you. Thank you. Okay. Yeah. So somehow I want to explain how those flat metrics relate to conformal or complex structures on surfaces. Okay. And when you have such a flat metric, so again, I'm being slopey with terminology. A flat metric should be something that's flat everywhere. What I call a flat metric is a flat metric with singularities. So sigma gn ends up with a flat metric. Well, a flat metric gives a complex structure on my surface. So away from the singular points, it's clear. And close to the singular point, you can see that there's always a unique way to write the metric in coordinates as z to the alpha times dz, with alpha, say, it's a bit technical, but it should be larger than -1. And so there is a unique, essentially unique atlas of chart where you can write the metric in this as with this formula. And so it should be this squared. And so you can extend the complex structure using this chart. And the mark points are just where the singularity lies. So to such a flat metric, you can associate an element of the moduli space. Okay. So this sort of invites me to. Oh, to define. Okay. So maybe I want to say something first. So when I've got such a flat metric, again, I've got the singular points. I've got n singular points, and I can associate it a collection of angles, which are the conangles I see at the mark points. Okay. So this is an important piece of data that I want to keep in mind. And with that in mind, I want to define, oh God. Oh. Sorry. I want to define T theta in the same way I define the moduli space, which is the set of flat metrics with angles theta on sigma gn mod isotopic to identity euphorisms, and m theta, so T stands for Teich Müller, and M stands for moduli space. It's the same thing, but mod orientation preserving diffeomorphisms. Okay. So it's not so clear what topology or structure I should put on those moduli spaces. I'm going to go back to this in a second. But based on this comment, that to a given flat metric, you can associate a conformal structure or complex structure with marked points, I see that I've got natural maps from T theta to the Teich Müller space, and M theta to the moduli space. It's just a forgetful map. And so an important theorem of Troyanov says that these maps, so you can call them F, maybe not F, psi prime, they're bijections. Okay. So it's a sort of uniformization theorem in a way. But instead of using hyperbolic structures for a given complex structure, you would use a flat metric with cone-type singularities. Why not? Okay. But somehow, this allows you to think of these two spaces in a different way. So, and that's why I like this identification. Okay. So maybe there's a comment I should be making here, because you could say, well, you've used theta here to to define your moduli space, but you haven't specified in the notation G or N. I mean, so I suppose N is given by the fact that theta has it in this definition, but G is not defined. So maybe you like differential geometry, and there's such a thing as a Gauss-bounded formula for Riemann surfaces in general, and in this case, there's also a Gauss-bounded formula. So when you have a surface with a flat metric, with datum here, we have that the sum of these curvatures at the singular points is equal to 2 pi times 2 minus 2g. So somehow the way you should think of this is the total curvature. So this is a flat metric, so you have no curvature, but all the curvature is concentrated in the singular points. And you could think of the function curvature being a Dirac mass at every singular point with a mass this. So you see that when theta I is equal to 2 pi, when the metric is regular at the cone point, there's nothing. It vanishes. Okay, and so theta carries the information of the genus. That's what I wanted to say, because you compute this. And so somehow this theorem should be made more precise by saying that those are bijections when these two guys over there are not empty. Okay. Good.
The condition for the unhappiness is exactly the Gauss-Bonnet.
Yes, exactly. Yeah. Thank you. Yeah. So it's a if and only if. Yeah, I'm not going to write it down, but when you have an angle datum that satisfies this Gauss-Bonnet formula for a certain G, then there is a surface of genus G with n mark points carries a flat metric with those singularities. Thank you. Okay. So somehow using this bijections, I can endow these two spaces with all the structures that you have on TGN and MGN. Or you can think of it as another point of view on TGN or MGN. That's the okay. So I talked about foliations. I'm not there yet, but I'm going to define the foliations I'm interested in terms of those flat structures. Okay. So that's why I need now to discuss a bit, in more detail, flat metrics on surfaces. And to do that, I'm going to use an example, right? Maybe I want to use some color. Red, yellow, and green should be good enough. Maybe I'm going to start with a square. I like to do that. And I'm going to draw two parallel segments here in red. And I'm going to require that they have same length. To do this here and this here. Can you tell the difference between green and yellow? No, maybe not. What about with? Not any better. Okay. What about blue? Yeah, better. Great. Okay, so yellow segments have same lengths, blue segments have same length, and same for red. Okay, so when I glue sides together along the unique isometries that map one to the other, I get a surface. It's a topological polygon, and when you glue sides of a polygon like this, well, you get a surface, and here it's not too difficult to work out that what you get is a torus. It's a torus, so maybe I want to just try and take a second to understand which are the points the vertices of the polygon that map to the same point in the identification. So this point here is identified with this point here, but by the blue identification is identified with this point here, which by the red identification again is identified with this point here. So there is a big dot here, and this point here by the blue and yellow identification with the cross is identified with this point here. Okay, and so I can see that my yellow line connects big dot to cross, and blue as well, and red is a closed curve that is based at dot. Okay. So why did I draw that? That's a flat metric, and somehow, so I don't want to convince you of this, but I'm telling you that's the way you should think of a flat metric. It's just a polygon, a Euclidean polygon, or a bunch of them glued together. There's nothing more complicated than this. And if you want to understand, well, so these points are the singular points of my structure. And you can convince yourself that if you go around these singular points, well, you will see angles that prevent the flat structure from being extended to an actual flat structure at those points. Here you can see that I've got an angle that's smaller than 2 pi. Maybe this is alpha, this is beta, or maybe alpha 1 I prefer, and beta 1. No, theta 1 and theta 2 if I want to stick to my notation, and this is P1 and this is P2. And on this picture, theta 1 is less than 2 pi, and theta 2 is bigger than 2 pi. And if you were to work out what the Gauss-Bonnet formula in genus 1 gives you, well, it gives you 0 here. So that would just tell you that theta 1 on this picture plus theta 2 is equal to 4 pi. That you would recover by working out the sum of the angles, the internal angles in a hexagon. Okay, this is the flat metric. Okay. Is there anything more that I wanted to say at this point? Okay. Whoops. Can't do both at the same time. No. So my ultimate goal, at least for the talk, is to introduce the foliation. My foliation is going to be defined in terms of geometric invariance on those surfaces. Okay, so I don't know, if you were working with a space of Riemann surfaces that you can identify with hyperbolic curves, well, you could take a geometric invariant which would be the length of the length of the shortest curve. And you could take the level sets of this function, and that would potentially define a foliation on the surface. That's something a bit of this kind that I want to do today. And the invariant that I'm going to use is the parallel transport of the metric. So if I take maybe parallel transport, so if I take gamma, closed curve, on sigma gn star, that's really when I've removed the mark points. It's too bad that now my picture's on top of the ball, but you could think of the map that maps the middle point of the red segment at the bottom to the middle point of the red segment at the top. That's a closed curve. And, well, I have Riemannian geometry at hand, so I can just compute the parallel transport along this curve. You take a little segment and you move it along, And when it comes back, well, it might have turned. It's a possibility. Okay, so I can define rho of gamma, which I can think of as an angle or an element in the circle or in a set of complex number of modulus 1. Well, I prefer the circle, so to use the circle, which is the angle by which you would have rotated going along gamma. Okay, this is well defined. And because my metric is flat, away from the singular points, well, this number only depends on the free homotopy class of gamma. Okay. Depends on the free homotopy class. Okay, and so if you wanted to work it out this way, you could think of rho as a function from the fundamental group of this surface, taking a base point, into the circle, and it's really easy to verify that this would be a group morphism. And because this group is abelian, then everything factors through the H1, the first group of homology, and you could think of rho as a map from the first homology group of sigma g and star coefficient in Z into S1. Okay. So this function, so maybe I can take a few seconds to try and compute this function on curves in this model. So if I take the closed curve that goes, let's say, roughly from bottom to top, crosses the red segment once, well, my two segments are parallel. So when I go along, well, when I come back, my parallel transport is trivial. Okay? But if I were to take the curve that goes from yellow to yellow, well, if I take, that's a bit of a shame, so I'm just going to reproduce this drawing just here. I take a curve like this, so these two sides are glued together. So I take a vector that's pointing downwards. When I arrive here, I'm gluing this back with this. So when it comes back, it will have turned by an angle, which is exactly the angle that those two segments form. And they form an angle pi over 2 because I inscribed my picture in a square. Okay, so that's, and you could do the same reasoning to find the same for the simple closed curve that goes from blue to blue. Okay? Very good. So this rho, sorry, so what's, okay, so this morphism rho, you can think of as an element of the H1 on top, sigma g and star with coefficients in S1. Okay, and so this I call the linear holonomy because, if you like the language of geometric structures, it is an invariance, which is called the holonomy, at least a remnant of this holonomy map. If you don't know what it is, just be happy with this terminology. And so this defines a map from T theta into this H1. S1, I'm going to leave a bit of room for some extra information that I'm just going to comment upon now. So this is a nice function. And the one thing I wanted to say is that if you were to take a loop that sort of goes around a singularity, so if, I don't know, C1 is that a loop going around P1, P1 is one of my two singularities here, well, almost by definition, rho of C1 is always going to be equal to E to the I to the theta 1. Or sorry, maybe theta 1 if I'm using this S1 as a to parameterize the parallel transport. Okay, so somehow if I fix theta here, I don't have too much of a choice, and I can't get every single element in this group, so I just have to specify the theta. I'm just saying that the target of this map is those elements in this H1, which map C1 onto theta 1, and if Ci is the loop around Pi, then it has to map it to theta I. It's nothing groundbreaking. And this, you could easily get convinced that it's isomorphic to S1 to the 2G. So essentially, because when you have a punctured surface, if you prescribed all the information around the punctures, then there's only the surface left, and the dimension of the H1 of a closed surface is 2G. Okay. And so this map is actually not defined at the level of the moduli space. Because to do that, you need an identification of your surface with a surface, and the H1 with the H1. And if you take a given surface, you need to be able to specify an element in this group. And if you take a given surface with a given structure, there are many different ways to identify it with a given model surface, which will give you, at the algebraic level, different elements here. What I'm saying is that this function is not invariant by the action of the deck transformation group for the covering T theta over M theta. Does that make sense? Okay. But the level sets of this function are still going to define a foliation that's going to be completely trivial at the Teich-Müller level, but that's going to be interesting at the moduli space level. So now should I put this? So, okay, so rho is equivariant with respect to deck transformations of the covering phi theta on M theta. And these are still, I'm insisting on that fact, nothing but TGN and MGN. So if you know and like Teich-Müller theory, I'm just saying that this function is equivariant with respect to the action of the mapping class group, which itself, with respect to the natural action of the mapping class group on the homology. Nothing but that. Okay? And so that this fact tells you that the level sets of this function are mapped to other level sets of this function by the action of this deck group transformations, and therefore I don't have a foliation yet. I need to say something, but if this were to be a regular function that would induce a foliation, then the foliation would pass to the quotient. That's essentially what I'm saying. So this is actually a theorem that's, I think, to be attributed to Veech. I'm going to write them down as facts, but it's not too difficult to prove, but it's a very nice remark from Veech that so rho is a submersion. It's actually analytic. Okay, and even nicer, so it defines the foliation on MGN, which is, in that case, through the identification with M theta. And the leaves, and that's probably what's the most remarkable fact of this foliation, that I'm going to call f theta, that defines a foliation f theta, are, I'm never sure how I should say that, but immersed complex analytic submanifolds. Okay, the leaves are complex analytic. That's with respect to the complex structure of the moduli space, even though it's not a holomorphic foliation. The foliation is defined by a function that's a submersion, but it's not. I mean, there are complex structures that you could put here, but it's not a holomorphic foliation. But it's still nice in some way because it carries a natural symplectic transverse structure. Okay. So this is what I call Veech isoholonomic foliation. A remark at this point is that I don't have only one of those. I have one for each datum of a angle theta that satisfies the Ghazouani formula. Okay, despite of, so here the space doesn't vary. I can fix G and N, and I can vary theta, and I will get many different foliations. Okay. Is there anything I want to say at this point? No. So maybe just say a few things about the most simple case. So that's nice because here I've got a genus 0 example. And in the case G is equal to 0, well, the dimension of the target space is 0. So my foliation actually is trivial. There's only one leaf. So G is equal to 0. Foliation is trivial. Okay. It's nonetheless a very important and interesting case because the leaf of the foliation, as we're going to discuss in a few minutes, carry very nice geometric structures. The G equals 0 case was studied by Deligny and Master, quite famous article. And in that case, the study of this foliation, I mean, which is trivial, relate to the study of the monodromy of some hypergeometric functions, and by Thurston in more geometric terms. Okay. So I don't know if there's, yeah. So now I want to tell you about what, so this foliation is interesting because, well, it's really something that you want to understand if you want to understand how those flat structures behave and arrange themselves in moduli spaces, but also because the leaves have nice geometric structures. So I want to discuss that a bit further now. All good. So an important feature of, I think, flat metrics is that somehow they're complicated because, I mean, that moduli space is identified with moduli spaces of complex structures, and these are known to be complicated objects. But in another way, you can represent them in very simple ways using polygons, and it allows you to have a more concrete grip on those objects. Okay, so to discuss a bit the geometry of the leaves. And to do that, well, it's nice that I have this picture here. So I'm going to, not to respect the natural ordering on this blackboard, maybe use this bit to carry on this discussion. But if I wanted to at least locally parameterize my moduli space, the entirety of it, and try to understand where is my foliation, how can I parameterize it, I would be very happy with this picture, because I can use very naively the complex numbers that are defined by the sides of my polygon. So here I've got 6 complex numbers called Z1, Z2, Z3, etc. Okay, well, and locally they define hexagons, and in turn those hexagons define flat structures. Okay, I've got some conditions, of course, on those ZIs. If I want them to close to a polygon, I need their sum to be equal to 0. Right? And I also need, so here Z1 is glued with Z3, so I need the modulus of Z1 to be equal to the modulus of Z3. And we can do the same, Z6 and Z4. I've only got 2 left, and that's Z1 and, no, Z2 and Z5. Okay. And at least locally, these equations may be up to, so maybe something, sorry. Something important I didn't say is that if I want this identification, T theta with mgn, I need to normalize all these flat metrics to have area 1 or whatever. Because if you take 2 metrics and you just scale them, you don't change the complex structure at all. So here maybe I always forget. That's terrible. Area 1. So maybe in this set of equation, I want to projectivize at some point, because also rotating is a trivial operation from the point of view of flat geometry. Okay, and in those equations, I'd like to understand my foliation. And what's very nice is that at the level of those equations, the equations of the foliation become even nicer. In the sense that, for instance, if I were to get stuck in the leaf of the foliation to which this example belongs, where the parallel transport between these two guys is the rotation by pi over 2, here as well, and here is rotation by 0. Well, these equations would become, so now I'm specifying the leaf. Well, the equation between Z1 and Z3 would become Z1 and Z3 form a certain angle and have same length. So that would become something of the form Z1 is equal to e to the I times pi over 2 times Z3. Well, depending on the orientation convention that you've chosen, maybe it's minus. I'm not sure. And so let's not check, so we'll never find out. And for Z6 and Z4, again, would be something of that form, plus or minus Z4. And for the last one, at least, if my orientation convention is this, would be something of the form Z5 is equal to minus Z2. Okay. And what's nice is that in these coordinates, which are very natural, the equations of the leaf become linear equations. And I mean, there's a way to make that formal, but those coordinates, they're canonical in a way. They come from, can define them in terms of algebraic geometry, and I will try to do that in a few minutes. Because if I was to take another sort of polygonal representation of this hexagon by maybe cutting off this triangle and gluing it back either here or there, well, the transformation would be linear. So somehow those equations are well defined up to some linear transformations. In a more geometric language, that would tell us that those charts, special charts, have transition maps that lie in a linear group. And since I've got these area 1 condition, then actually things are projective. And this discussion, so maybe I didn't write down all the details, but essentially you tell me that my leaves, they have leaves carry projective structures, complex projective structures. And this is somewhat nice. And you can actually go a bit further than this, because you have, in those coordinates, you have a function which is the area of the polygon that you're working with. And this, again, is going to be preserved by nice natural transition maps, which consist in cutting and pasting triangles and shuffling them around. And so the area form, let's put it like this, in coordinates z1, z6. So I hope you're not too confused by the fact that I'm dealing with an explicit example, torus with two singularities, everything generalized to arbitrary number of singularities, is a Hermitian form. It's a Hermitian form. And so this tells you a bit more. It actually tells you that this projective structure, I'm not going to give too much detail about this, specifies into a, instead of just being projective, I have some what people call complex hyperbolic spaces with a signature, so which are essentially manifolds which are modeled on this subset of the projective space of dimension p plus q. Essentially, so you have a Hermitian form. It's going to have a signature pq, and you can take the cone, the projectivized space of the cone for which this area form is positive. I don't want to give too much detail on this, but I mean there's a bit more in terms of structure, and you can work it out. And this structure comes from the area form. Okay. And that's somewhat nice. So maybe I need to say a few words about how you can see that in a more algebraic way. So, yes. For those who are completely allergic to, let's say, flats and combinatorial geometry, the way you could think of a flat structure, if you look in those coordinates, you can look at the one form dz and see how it extends to the surface. Okay, and a way to think of a flat metric, so flat metric is a one form, omega one form, over a Riemann surface with value in a instead of taking values in C, a value in a flat unitary Lamb bundle. Okay, so that's the way to see it. And when you integrate this form with respect to the flat connection, that gives you a local identification with C, well, you will find those charts that will define the structure. Okay, but that gives you a more algebraic viewpoint on this. And somehow this foliation and this rho corresponds to rho, fixing rho, say, corresponds to fixing this line bundle and the flat connection. The flat line bundle. Okay, and so now when you fix the flat line bundle, when you have such a one form, it defines an element in the cohomology of this line bundle. Okay, so defines an element in the cohomology of this line bundle, and those coordinates are just an explicit way to describe this element in the cohomology by integrating your one form over some special cycles. Okay, and this area form, so maybe you can say that these Z1, Z6, or Zn correspond to an element, let's say omega, in the H1 of for the let's say local system defined by this flat bundle. That's a way to think of them. And yes, and so the arrow form comes from the cup product on this H1. So somehow there's a way to work out all this structure. And anyway, but what's nice is it gives some nice structure on the leaves, and in a sense, all this structure allows for some better understanding on the geometry of the surface. So I've spent about 15 minutes trying to define those foliations. So if you've followed me up until then, thank you very much. So now I'm going to talk about maybe some results that I have in collaboration with Luc Pirio, and some like general question that you might want to ask on those foliations. Unless you have question now, I'm happy to address if I can. Okay. So joint work with Luc Pirio. We study the G equal 1 and N is about equal to 2, meaning that we have a lot of results in the specific case N is equal to 2, and we have some more general but weaker result in the arbitrary N case. Well, okay, so in that case, M12 is a complex surface. And the foliation above is a foliation. I mean, this family of foliation, each of them individually is a foliation by a complex curve. Okay. And so somehow you should believe that if you care for flat surfaces, or even for the geometry of complex curves, these foliations are of interest. And once you're convinced of that, well, the first question you might want to answer is understand what are the algebraic leaves of the foliation. Are there at all any algebraic leaves? So question 1. It's not a question, let's say it's a problem. Algebraic leaves. Do they exist? Who are they? How many are there? Okay. The existence of algebraic leaves in some cases, from a purely geometric viewpoint, is not too difficult to establish. Because when you take theta to lie in a finite subgroup of the circle, which means that they're all rational multiples of 2 pi, and that you force this invariant rho to do the same thing, basically that rho that you can think of a morphism has finite image, then you can show by a rather simple geometric argument that the leaf that corresponds to this rho is algebraic. So you can prove a bit more. So maybe with Luc we have this this theorem that tells you that for any theta, so it doesn't require this this heavy assumption on theta. So for any theta, g equal 1, n equal to 2, there are infinitely many algebraic leaves. Okay, so their union is dense. And so you can list them, and they are isomorphic to the those special modular curve, where this is a congruent subgroup. Can't remember what you call them. But that's basically it. And the question is wide open in genus, arbitrary genus. So somehow, and from a purely geometric viewpoint, I suppose for foliation people, the existence of such foliations is not a surprise. But from the geometric viewpoint, the fact that when theta is not rational, you can have those algebraic curves is very surprising. And we have absolutely no understanding at this point of what they mean at the geometric level. But that's one nice question. Okay, and so in the general case, even finding one algebraic leaf in one foliation for which theta is not stupid would be a very nice achievement somehow. And then, well, depending on come from, you have dynamical type of questions. So of course, the question of the dynamics of this foliation is very interesting. So, and again, they would tell you a lot, at least some information about the geometry of the surfaces. So, dynamics. So maybe it can tell you. So I think the case G equals to 1, n equals to 2 is sort of a maybe example that sort of points at what the answers should be. So again, with Luc, we have the almost every leaf is dense. That's one thing. It's a bit more than this. So you have a transverse symplectic structure and therefore an invariant volume form, transverse invariant volume form, and the foliation is ergodic. In spite of having closed leaves. It's a bit stronger than this, so it satisfies some sort of Ratner types of theorems, for those who know what this means. It tells you that essentially when you have an orbit, a leaf, it's the set of accumulation points is nice in the sense that it's either the whole space or a nice closed submanifold, analytic submanifold, or a type of phenomenon. And again, I don't know how to prove anything in the more dimensional case, higher dimensional case. So many of the questions. So, can you prove any of those statements in the more general case? And so maybe one last thing that's more of interest, I think, to people who care about geometric structures is that using this discussion on the geometry of the leaves, you can endow the whole space with a volume form that's only depending on the thetas. And it's an open question to know whether the volume of those moduli spaces with respect to these volume forms are finite. And you might not care for these questions, but for the understanding of the geometry of this flat surfaces, it would be an interesting question. And again, the answer is yes in the case of the genus 1 and n is equal to 2 case. And more than that, the volumes satisfy some very nice recurrence properties, and it might be possible that you can interpret them in terms of cohomological classes of those moduli spaces, but at this point, very little is known about these. So, okay, I think I'll stop here. Thank you for your attention.